The pattern you may have noticed, so if we have x plus y to the 6, we would have to go to Pascal's triangle to row 7. I shouldn't have picked such a big number. I'll change it back to 5, because I've got that already. There we go, not such a big number. And what have we noticed so far? Well, we've noticed that the coefficients come from Pascal's triangle. 1, 5, 10, 10, 5, 1. Your first value there, x, starts with 5 of them and goes down 1 each time. Your value here, y, starts with none of them and goes up 1 each time. In each term, the exponents add up to 5, because that's your power that you have right there. So now, how do we write this in a general way? The binomial theorem using combinations, this is the general way. If we would have showed you this first, you'd be like, ah! But it's not so bad if we break things down, especially if we color code it. Okay? What do we know about each of these numbers? Well, this is 5, choose 0, 5, choose 1, 5, choose 2, 5, choose 3, 5, choose 4, 5, choose 5. Those numbers in front, whatever value of n that you have, you start with n choose 0, n choose 1, n choose 2, n choose 3, until you get to n choose n in the end. Then, in blue, we looked at whatever our first term is. Well, we start with x to the n of those. And then we go down 1, then down 2, then keep going down until you're down to 1 and you have none left in the final one. And if we look in red, what happens to our second power? Well, we don't have any. We start with 1, then 2, then 3, and we keep going up until we have all of them in the end. And this is the pattern that happens. We're not going to use algebraic expressions, because all they did was expand the combinations formula and made it look even worse. Okay?
It looks smarter.
So this pattern of our one term in our first term in our binomial going down by 1, our second term in our binomial going up by 1, and the numbers in front from Pascal's triangle from combinations help us solve all of these expansions, even if we have two different things inside as our binomial. So we're going to expand 4a squared plus 2b to the power of 3. Well, to the power of 3 will mean how many terms? 4 terms. So we go to Pascal's triangle. Where we have 4 terms. Our first value inside our binomial is 4a squared. So how many 4a squareds will we have to start with? 3 of them. And then we'll have how many 4a squareds next? 2 of them. Then 1, and then none. Our second term is a 2b. How many 2b's will we start with? None. And then 1 of them. And then 2 of them, and finally 3 of them. So we use this as a setup, and then once we've set it up, now we can simplify, because it does say simplify in the end. So this is going to equal, to use our exponent laws, 4 cubed is 64, a squared cubed, a to the 6, plus 4 squared is 16, times 2 is 32, times 3 is 96. We'll have a squared squared will be a to the 4, and then we have a b. 2 squared is 4, 4 times 4 is 16, times 3 is 48. 2 cubed is 8, And there is the simplified form. Number 7 for practice.